Hi and welcome. So today we're going to be covering introduction to series and parallel circuits, and our goal really is how we're going to solve the circuit receipts here, right? What strategy we're going to use, where do we actually, corners we start from, what's a voltage source, how do we treat resistors? There's a lot of questions, and hopefully we'll have lots of answers by the end of this session. So we're going to quickly get started, and again, we're going to do series first, followed by parallel, and then tackle our way down. And again, here's our goal. Our goal hopefully is hopefully done a little bit of reading about circuits, but I'll go over it in detail. And again, to make life easy, I love to always include numbers, and numbers makes things a little more fun and hopefully exciting and something to strive for as we move forward. And as we look at that, here is our strategy, right? Is okay, as we have series and parallels, that means that you need to understand what a basic series circuit is first, and what a basic parallel circuit is as well to get started. And the series circuit, although simple, has a lot of details in it. And if we start off here, which is an example of our simple circuit, this one has three sources of R1, R2, R3. Three resistors and one source. R1, R2, and R3 are resistors. And again, depending on the textbook you've been looking at, you might see voltage sources to be drawn on the left, or voltage source to be an example of the one that you see on the right. Either or are actually totally fine to use. You might see sometimes I use that, sometimes I might use this. It all depends on the actual problem. And we're going to be talking quite often about our good friend the resistor, and I'm going to try to highlight the wires, not given much attention, but hopefully by the end of today you'll give a better sense of how important it is to have a starting point and an ending point to just a simple wire as well. All right, so what's the big picture again? And it doesn't really matter about what circuit problems you're looking at, but the goal hopefully is that no matter if you have a complicated looking circuit, say this is a complicated for now, although you'll hopefully think this is easy later on, our goal is to always reduce it to simplified circuit, or aka our ideal circuit, where we're going to have just a voltage source and it's R equivalent or RT. I'll either call it R total, which is R underscore T, or REQ, which is R equivalent. They kind of mean the same thing in my world, so let's keep moving from there. All right, so again, to tackle these problems, looking at just the simple case of having a series circuit, and the series circuit as you see here, the most important thing to remember for all of circuits, in fact, is the relationship between voltage, resistance, and current. And then they're given abbreviations or symbols as well. So the first abbreviation is just V for voltage, R for resistance, and I for current. So we can take those three values, right, as we saw here, and the relationship between the three is something important, and possibly the one thing you should never forget when it comes to circuits is really Ohm's Law, named after George Ohm, a physicist. And that relationship, he proved that voltage is proportional to current and resistance in this fashion. In other words, V equals IR, and just that alone can help us solve for all different types of problems. And no matter how complicated, Ohm's Law is going to be our backbone. We can always reach back and hopefully use that to solve for or address any problem. So with that, we're looking at a problem in its very simple form. You have one voltage source, one resistor, 20 and 10 respectively, and there's going to be a current that's associated among it based on Ohm's Law. Now that proportionality is again a fraction, and as you can see here, that fraction is just, if you're given Ohm's Law, V source equals to current times resistor, it's going to be equivalent to this proportionality of voltage over resistance will give us back our value for current. So in other words, if I did the 20 volts over the 10 ohms, I get back current. So for this particular example, I get back 2 amps. 20 volts over 10 ohms gives back 2 amps to be a current that's going through the circuit. Due to convention in circuits, the current, we're calling it leaving the positive end of our voltage source, will be our current. And then that, because it's leaving in that positive end, we're going to dictate that to be a positive clockwise direction. Current has flow, it only has direction, so it could either go clockwise or it can go counterclockwise. We'll talk about direction as we go along the way, but as far as a path is concerned, it has those two options. And when we look at our circuit that has, say, 3 resistors, we're just going to modify Ohm's law a tad. And to do that, we can do our, and again, we're going to put numbers down to make our lives easy. Here's our Ohm's law equation. That's V equals to IR. We have a 10 ohm, a 20 ohm, and a 10 ohm resistor in our 20 volt source. This adapted version of it, you can also write it as the sums of all the voltages will equals to I times by the sums of all the resistors. So let's talk about why these are sums and the current is not a sum. Well, the idea is that because this is a single loop, the current, this charge, right? Charge over time is what current is, dq over dt. It only has one path, so there's no way else for it to go. So it is locked in. So in other words, the current is shared among the 10 ohm, 20 ohm, and 10 ohm resistor again. And it's going to continuously go in this clockwise notation for this particular problem. All right. So for convenience, you can see that the sum of voltage, we only have one, which is 20 volts. It's going to equal to the sum of all our resistors, which is the 10, the 20, and the 10 again. Will give us back the 40 ohms, right? 20 volts, and we can see that for a simple circuit problem like this, we get the 20 volts over to 40 ohms gives us back the 0.5 amps. Is what's going to be moving, traveling, charge, dq, charge over time over the circuit. But let's deep dive a little bit more. So remember I said that the system here, one of the things we should get out of here is that that in a series circuit, or circuits, all circuits actually, the energy, the system is conserved. And how is that system conserved? We'll talk about power some other time, but there's power associated with this. There's this conservation of energy that's associated with conservation of voltage and also the conservation of current as well. We're going to talk about how that entire system interplays with each other. So again, wherever we get into circuits, really the question is, where do we start? A good starting point for me is when I think about, I'm showing this in a simple circuit, so when we get to more complicated stuff, we have a game plan. But I like to label it just at first to get a feel for it. I have A, B, C, and D as my edges here. I always like to start for underneath of my voltage source, right? That's how I start. This is again recommended. So I recommend to start at A. And I recommend that we're going to go clockwise notation, this particularly when we have a positive sign here, which means the current's leaving here is going to generate this clockwise notation. We'll talk about it when it goes the other way some other time, but for now, let's keep that what our recommendation is. Then again, we're going to be recommend reading our components. A component again is a voltage source, a component. A resistor is a component, and if it's entering, right, it's going to affect the polarity. So what we're going to talk about, what's entering what, is really the goal. So again, there are two different types of devices, right? We talked about our voltage source and our resistor. Our voltage source has polarity inherently, as you can see here. Polarity means that it has a poles, negative and a positive. A resistor on its own, a resistor on its own is just a passive device. It doesn't have polarity. So I put a resistor on the table and just looked at it. It's not gonna say positive or negative. If I use a meter to try to measure anything related to it, it shouldn't show anything, right? Because it's only gonna show resistance, especially when I'm measuring on the table. Again, it's a passive device. It has intrinsic properties inside of it. In other words, it has a length, it has an area, and it's related to rho, which is the intrinsic conductivity of the element inside of it that affects its resistive properties. So again, these are all intrinsic things, but a source like a battery source, our reactions, they're actually generating this poles primarily because of this energy that's stored within that system that's providing that push. And when you have that energy, it has this net positive and negative that creates this level of energy, which is called our potential difference between those two terminals. Okay, all right, so getting an idea about that. So when we're looking at these problems, right, Yeah, but these elements again, sorry, there's an issue here with the screen, but the idea again is that because I know that this is a given, negative, positive, I can label it negative, positive, right? What's important here is if the current is entering a passive element, we'll give it the sign of a positive. So here is my terminal. It's the current's leaving always from the positive side. So because it's entering a passive element, I'm going to put a positive in front of it. The current continues through, right? Then a negative on the other side. Then it's entering this side. So I give it a positive, then a negative. Then it's entering this side. So I give it a positive, and then it leaves the negative, and then back again to the negative side. So again, if current entering a passive element, then we're going to call it positive. Okay. Current leaves from the positive terminal of our voltage source. All right, so we're going to try to keep these two rules when it comes to dealing with passive components like our resistors. Really important. Okay, so now that we have that, we can try to label this stuff in blue. The always are given is a negative and positive based on the terminals of our voltage source, which have poles. Our resistors as passive devices do not have poles, so we will give them their convention based on the flow of the current. So it's leaving the positive ends, entering into this resistor, getting the positive, leaving, entering this resistor, the main current, right? And then this positive, negative, it's entering this side, so it's positive on this side, leaving, and then back. And we can write down a really fundamental conserved equation, which is our KVL equation, which states that the sum of all the voltages must equals to 0. So that's what the conservation is here. It's conservation of energy. We'll talk about energy more on the power side, but again, voltage is embedded into power. So what this means from a mathematical standpoint is I could write down an equation that solves this series circuit to net to 0. I start off from A, and then when I go from this value of A, we can read it as minus Vs plus Vr1 plus Vr2 plus Vr3 equals to 0 will be my equation for my Kirchoff Voltage Law. I'll state it one more time. Because I'm starting at point A, I'm reading the signs that I enter into each component. I'm entering the negative side of this source, a voltage source, I give minus, entering the positive side, entering here, it's positive, entering this side of this component, it's positive. So I have minus plus 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 equals 0. And that's how you would write that KVL equation down, okay? Now, let's try to solve this, right? Because one that was obvious to us is this minus 20V, right? Minus 20 volts. Then others we're not quite sure, but let's think about that. What they must be? Well, by definition, they're going to satisfy Ohm's law. So because they're satisfying Ohm's law, it's minus Vs, which you know is minus 20 volts. The second Vr1, Vr2 all must also solve for using Ohm's law. In other words, V equals IR for each one, but it's specific now. So it's Vr1 equals to I, notice all the I's are the same because they're all the same for each, times it by R1. Vr2 equals to I times it by R2. Vr3 equals to I times it by R3 will be our approach for this particular problem. So because of that, we can simplify this problem, right? It's going to be minus 20V plus I times it by R1, which we know R1 is called 10 ohms, right? And then R2 is 20, so we I times 20 plus I times 10 equals 0. So if I simplify this problem, it's going to be minus 20V plus I40 equals to 10. And here's a small blow up of the problem. So again, minus 20 is going here. And I have the current the same for every resistor in the series circuit. So it's that value of I times it by the first resistor that I see, which is the 10. And the same current times it by 20. And the same current times it by 10. All of it nets equals to 0 is what KVL's equation states. So because of that, I can now solve this problem, and I get back that I of 20 equals to 20 volts. By moving the minus to the right hand side of the equation, I get back I equals to 0.5 amps. It's going to be the current through my circuit. So again, hopefully it's not so bad. This is the picture again as well, right? No polarity for these for resistors. They're passive, but however we can guide them, right? We can determine their sign convention based on the flow of the current is what we're trying to do. And we're simplifying these problems to get a solution of that 0.5 amps. Okay, so we can always do a check to see if everything worked out. And the strategy again is that we know that we have a minus 20. We know that we have our 10 ohms, right? And we know we have 20 ohms, another 10. So we're going to do Ohm's law at each side. Get V of the 10 equals to 0.5 amps times about a 10 ohms. Gives me back 5 volts. Is my voltage between B and C. That's my drop. Okay. So this is called, if you're going from a negative terminal to a positive terminal, that's called a voltage rise. If you're going from a positive terminal to a negative terminal, that's called a voltage drop. Okay, so I'm having a voltage drop of 5 volts, 10 volts, and 5 volts again by using that strategy. Okay, so the important thing to take out of this is that the currents are the same in the series circuit. Okay, and again, for series circuit, you can use Vx equals to X, meaning our unknowns, equals to I is the same everywhere, times by R of our unknown value. Also remember that the sums of the voltage equals to 0 in our series circuit. And I generally start from point A, right, to help me get started. And I write an equation that shows that it should hopefully come out to be 0. And if we did our math again, minus 20 plus 5 plus 10 plus 5, and that's 0. So our check holds true, that it satisfies our KVL equation. So our problem looks good. Okay, so that's how you approach that. All right. Another way of approaching these problems is that we could also use something else called voltage division. So working on these problems, okay, voltage division states the following. This is a general equation. Vx equals to Vs times it by Rx over Rt, or you can call it Vs equals times it by Rx. That's a typo there. I'm going to fix that for you. So it's going to be here Rx, our unknown, times it by over our equivalent. So here it is again. So if you have an unknown value, a voltage that you're trying to solve for, you call it Vx. Our source voltage is our Vs. Our unknown resistor is our Rx. Our total or equivalent resistance is on the denominator of this proportionality. And then now we can solve this hopefully a little bit faster for a series portion of a circuit. So here we have the problem again. Say that we did not solve for I source right off the bat. What we can do is we can use voltage division right off the onset of this problem. I'm going to try to attempt this. Again, notice that before, the first way we solve this series circuit is we solve for the current of the entire circuit, our I source first. Then we solved for the voltage across each of these resistor components. But we didn't have to do that. We could have also used voltage division right away and then solved for the voltage across each of those branches. So let's try this out. We can try to solve for VR1, VR2, or VR3 using voltage division that's used for series portions of circuits only. So if we wanted to solve for VR3, right, that's our 10 ohm on the bottom. This is how it looked like. We use this equation that I just showed you before. And then once we have that, right, we identify it here in green. So now I'm just going to plug and play. I'm going to take my unknown resistor, value that we're trying to solve for, which is 10 ohm resistor. Our total or equivalent is going to be the sums of all those resistors, because this only works for the series circuits, the 10, the 20, and the 10. That's going to give a total of 40 ohms, and our V source is going to be a 20 volts resistor. So to solve for the voltage across the 10 ohm resistor is going to be 10 ohms over 40 ohms times it by 20 volts gives us back 5 volts. Okay, so that's pretty handy. So you don't have to solve for the current right off the bat if you didn't want to. You can just simply use voltage division when it comes to solving of that as well. And again, I showed you for the others as well. So if you want to do V10, it's the same strategies as well. If you want to solve for the 20 ohm resistor, same strategy. This time you put the 20 as the resistor you're trying to solve for. Your same total, because it's a series circuit, the same source, because the same source voltage, you get back 20. So this is also nice, neat, and elegant. So you can solve for the voltages across each of resistor components without too much headache, which is kind of great. And it makes your life easy. So where do you start now when we get back to this problem again? Okay, so now we're finally getting there, and we have to tackle the series circuit to get a better feel for a series circuit. So now we got to get a better feel for this problem. And at this problem, first glance, if we covered a portion of the screen, you'll notice that here is just a series piece of puzzle, right? Then something happens, right? So let's think about this very slowly. So your charge leaves the positive end, it gets here, it goes across the 20 ohms, and it reaches this junction point. It's a split. It's like a divider in the road. That divider here, some of the charge is going to go this way, and some of that charge is going to go that way. Okay, so it's a junction. Right, and if you think about it as water flowing, if you have water flowing through a pipe, some of it's going to go, it leaves the main, or think of it as like an above ground pool. The water is going to flow here. It's going to leave through this main pipe, and then it's going to reach this junction, and some of it's going to split here, some of it's going to split there. Because it splits, we're anticipating that the current, the charge, will be splitting off. So it may not be the same current that's here versus the currents that's going through here and here. So let's find out what's actually going on. Okay, so remember again, we're trying to reduce this circuit from a big circuit to hopefully something ideal, just one source and one resistor and one current source. Okay, so to do that, we're looking at this, and now we're going to start adding vocabularies to get a little bit more familiar. So the charge leaves here again, and it splits off. It's entering this junction, then it leaves, then it all comes back over here. They actually recombine again, and when they recombine, notice the arrow. So the arrow of the current goes here. The current that was on the top branch, it goes here. The rest goes back there. Okay, so what we expect is that this is how it's going to move. Again, just if you use the water analogy. And to give some more vocabulary, where it splits, or where this junction is, it's called a node. Okay, that's what happens. So you have two nodes here, a top node and a bottom node for this particular problem. And we're going to give it an arbitrary name. We're going to call it letter A. And you're going to have a bottom node, right? And they usually call it ground or your reference node. Okay, so that's generally what they call either or case. So now, when you have that, to get more vocabulary, between these nodes, they call branches. So in yellow is an example of a branch. You have, and then green is also a branch, and the pink is also a branch. You have three branches, and they all attach to those two nodes, nodes A and then the ground node on the bottom. So how does this look like? I like to draw it another way for convenience, because it helps me visualize the problem a lot easier, hopefully. And you can see now that if I was to draw it, remember, a wire is a wire. It's fairly flexible. It doesn't have these jagged edges all the time, right? That's just some ideal mock-up just for convenience, and it helps us, the students and people working this electrical field here, to get the feel for it's more convenient to draw and more eloquent, of course. But realistically, a wire is flexible, right? It doesn't always have to be stiff and rigid. So you can look at it this way as well. Take a moment to see if you can visualize this. And the idea again is that you have your voltage source. That means that the current, your current here will do something. So it can potentially do this, right? You can have your current coming up towards this node, and then when it reaches that node, then the rest are going to flow like this. Right? You're going to have one going in from the source, and the other two going down towards ground, and they're trying to get back to ground, and aka back to the negative end of your source as well. So I like to think of it this way too. So when I'm looking at these problems, I have three visuals in my head. When I'm looking at this A here, right, and ground here, I'm thinking of it as well like this. I'm looking at it as A to ground, A to ground as well, and those are 3 different branches. But the nice thing about those branches is that you could analyze anything within those branches independently of the rest of the circuit, which is kind of hopefully important later on and hopefully important now. So what does that mean? When I look at this problem, right, I could simplify each of those branches if possible. And in this case, it is. So I highlight here in green, the 7 and the 3 ohm resistor are on the same branch. So I can do whatever I want of anything on the same branch. What that means with the 7 and 3 is I could actually combine them, because in that one particular branch, there's just a series circuit, right? So as you can think of it as series, I can combine that to make that 7 and 3 and just call it 10 ohms right off the bat. So now I have 3 branches, a 10 ohms, and then the 20 ohm and 15 volts in series with each other. It'd be really clever to think of it this way, because later on it's going to help us out a lot. So again, if I recombine that circuit, the circuit is going to look a little bit more like this. I can have it simplified to the one that's on the right, which is this variation of the circuit here. And I can always draw it back to the more rigid rectangular version of it, I suppose, if that helps us go back to this form. And that version of it is this here, right? So here's a nice reduction of our problem so far, to reduce it to something that's a little bit more, hopefully, easier to work with, okay? So again, we're still trying to get here. We haven't given up on our dream to actually reduce it down to a voltage source, a current source, and a resistor in that fashion. But then the question is, okay, then now we have this issue that's new to us, is that these two, because of that split, because of this junction here, anytime you have a junction, it creates a new word, which is our parallel branches. So some branches are in parallel with each other. So how do we do that? Well, we can dissect this problem by literally considering cutting off this piece, right? We can split it. So I have this 15 volts and this 20 ohms that are in series with each other. Then I have the 10 ohms and the 10 ohms over here, which are what's called in parallel to each other. So anything that's in parallel with each other, we can actually reduce it down to something more simple. So we're going to reduce it down. And to reduce it down, here, these are actually double slash lines. Looks like the number 11, but they're actually 2 parallel lines. That's my code word for parallel. So to do that, the definition of parallel, you can just do the equation for that. To simplify a parallel to one resistor is to do 1 over R1 plus 1 over R2 plus 1 over R3 plus infinitely, right? You're going to sum up as many resistors as you have, as you can sum them up. And then you're going to be left with something hopefully equivalent to the parallel piece. So if I do the 1 over the parallel piece, which is the 10 and the 10, I'll have the 1 over 10 plus 1 over 10. That's a mouthful. That simplifies to 1 over 2 over 10. And I flip that, I left the 10 over 2, which equals to 5 ohms. So in other words, I can replace the 10 and the 10 ohm resistor and simply just call it a 5 ohm resistor, right? So now I have a simpler version. So I have my original piece, which I cut the left cut, and I can now simplify the right cut and just call that 5 ohms. So when I put them together, that's something nice and simple, right? Because remember, our goal is to simplify our problem. Our goal is to have this. Our goal is to have here the 15 volts, and then our equivalent, or our total, which is going to be our 25 ohms, right? 15 volts, and then our current I source, right? So if we did that, we're going to be left with the 15 volts, right? 15 volts equals to I times it by the sums of all the resistors. Remember, there's no sum of the currents because there's only one current in a series piece. So 20 plus 5 gives me back 25. So 15 over 25 gives me back 0.6 amps. So I get back 0.6 amps is what's actually flowing through this entire series circuit. It's going through this like a highway, right? It's going or NASCAR. It's going NASCAR crazy right around this loop. And here it is as well. It's going through this as well. And then we can see the 0.6 amps just riding around this continuously, which is great, which is wonderful. But now that we know those three values, now we say that we wanted to take this problem a step further, right? We simplify the problem. We figured out what the source current is, but we could also have asked you a few more questions. We could also ask you what the voltage is across a 20 ohm resistor. I could have also asked you what the voltages are across both the 10 ohm resistors as well. And the question is, how do we do that? Okay. So to do that again, and here's our original problem. We had three branches. This branch, middle, and on the right, and I simplified it to the 5, right? So I took this circuit. You notice the 0.6 leaves our source. The 0.6, make sure I don't forget my convention signs again. It leaves, that's the voltage source, and it leaves there with 0.6 amps leading the charge, right? It's like kind of literally saying, I'm the source. I'm now pumping out 0.6 amps. It gets here, and then it splits off. Or I can leave it as a 5 amps, because in the 5 ohm world I can see that the 6 just rips through it and then it leaves back as 0.6 and enters back in. But let's look at another visual of this, which is probably a little more important in my opinion. Let me clean this up a little bit so you can see it a little more neatly. So what's happening now, so just clean this up so you can see it as I talk, is that 0.6, and try a different color. The 0.6 is going like this. 0.6 amps. It's leaving the source, voltage source. And then when it finally gets here around this bend, it's going to reach this junction point. And then some of that is going to split here, some of that's going to split here, and then it's going to reconvene, right? And then it's going to go back, and then it's going to be the 0.6 again. So temporarily it breaks apart or splits. So let's look at this. So what did I do is that here, we move these pictures a little bit closer to each other. I redrew this picture over here. Let me shrink it down so you can see it. So these two circuits are equivalent to each other, right? I like the one on the left way more because it shows this split. So what split does it show? It shows this junction or this node where they're attached, and they temporarily split into this side of our 10 branch and then this side of branch, and they reconvene. They reconvene here, or sorry, technically here, they reconvene in this world, and they combine here in this world, and they go back to the 0.6 again on this portion of the wire all over again. It's only a temporary split. So think about this as water. So if you had a pool, and in your pool leaves from a large pipe that's 20 inches wide, then it gets to a junction where there's two pipes. One is 10 inches wide, one is 10 inches wide, and they're going at 0.6 gallons per hour. Hopefully our instincts say, because both pipes are 10 inches and 10 inches, that there'll be equivalent amount going through both sides. And then they're going to recombine here and then back to a 20-inch pipe over here and then back home, right? To the ground side, and continue this cycle. So hopefully our instincts say that because these are both the same diameter of 10 inches and 10 inches, that the 0.6 temporarily splits to hopefully 0.3 and 0.3 gallons, and then reconvene here back to 0.6. Hopefully our instincts are right, so let's try this out. So we will hopefully learn some new things today. Other things that we'll learn is that the sums of all of the currents that are entering, right, a node must equal to 0. The sum of all the currents entering and leaving a node must equal to 0. And that's really important. I actually give it a name. It's called Kirchoff's Current Law. Again, it says the sums of all the currents entering plus the sums of all the currents leaving a node must equal to 0. So let's try this slowly. On this problem, you have 0.6 amps entering this node, right? And then the entering and then leaving this node, we have current leaving this 10 ohm side, another current leaving the 10 ohm side as well. Okay, so it would look like this if you were to force to write that. And again, we can call give it a sign convention. We can say that the ones that are entering the node to be a negative value, and those that are leaving to be a positive value. So I can say that I have a minus 0.6 amps entering this top node, and I have plus the current of the 10 ohms that's going down the left branch, plus the current of the right branch, 10 ohms, what must equals to 0. And that's called KCL. Another form of it. So this is what KCL is trying to say. Okay, so let's see if it's true. So sums of all the currents entering or leaving a node must equals to 0, and it follows hopefully a nice tight equation. And we learned about Kirchoff's voltage law. So there's also something else called Kirchoff's current law, as I said earlier. But then there's also called this equation here to solve all that. It's called current division. Okay, and for current division, I go ahead and use this equation, right? So the equation says here, importantly, you should use this one all the time. It says the current source, I current source, is R total. This is very important, but it's R total only for parallel. Parallel portion. That's why I put these little double lines. So over here, this is actually not the number 11. This is double lines, meaning parallel, or lines next to each other. So that means parallel. So keep that really carefully in your notes that you're going to have here. So then your current source times by the R total of your portion of your circuit that's only parallel will equals to I of your unknown current source times it by a resistor of the unknown or the one that you're trying to solve for. Okay, let's try this out in practice. So if I wanted to solve for the current through, remember they both are 10 ohms, right? They're both are 10 ohm resistors. If I want to solve for the current through one of the 10 ohm resistors, this is how it's going to look like. It's going to be, we know the source current is 0.6 amps. We know the total resistance is 5 ohms. How do we get the 5 ohms again? Well, we did the definition of parallel, which is 1 over R1 plus 1 over R2 equals to R of the parallel piece. So in other words, 1 over 10 plus 1 over 10 will sum up to be 5 ohms. That's what we did earlier. And if I wanted to know the current of, say, the current of the 10 ohm branch, well, they both 10, so it doesn't really matter, and Rx of the 10 ohm branch, so then we're going to use that equation, which is over here, and we copy and paste this to move it so you can see a little more clearly. It's going to be this. It's going to be I source, which is the 0.6 amps, times by R total for the parallel piece only, which is the 5 ohms, equals to the current of, which is we don't know yet, which is our I unknown of the 10. I put 10 as a subscript to remind you, and it's R of the 10 ohm resistor. So 0.6 times by 5 ohms, a current times by a resistor gives me back a voltage, so I get back 3 volts, equals to I10, which I'm trying to solve for, times it by 10 ohms. So the current of a 10 ohm resistor is going to be 3 volts over 10 ohms. So 3 divided by 10 gives it back to 0.3 amps. So instincts were correct. So if the both pipes are the same or both of the resistors are the same, they're going to equally have 0.3 amps going through each of those branches independently of each other, which is pretty cool. So the entering will be negative, the leaving will be positive, and we can write down, see if our KCL equation is correct. Because remember, the sums of all of our currents equals to 0 is what Kirchoff's current law states. So if it's entering, right, so let's see here. And again, it depends which node we use. If I use the bottom node of this here, then the ones that are entering are the minus 3 amps, right? And the minus 3 amps, what's leaving is positive, then it's be the 0.6 amps, then I get KCL is true, that KCL is 0, which means I did this correctly. If I use a top node, right, then if I use a top node, which is this one over here, right? So then that top node, then it'll be minus 0.6 amps plus 0.3 plus 0.3 equals to 0. So it doesn't matter which node we use, the KCL still holds true. That KCL is, as our backup proves that this is correct. So again, now that we know how to solve for the currents of each side of the branch of the problem, we can also find the voltages of it. So to find the voltage of it is just going to be the voltage of say the V of the 10 is, we solved this, we know the current with our branch is just using Ohm's law. So Ohm's law again states that we're going to have V equals to I times it by R. So the current of that, only that branch, is 0.3 amps. And you multiply it by the 10 ohms, gives us back the voltage of 10 is 3 volts. And then between the 3 volts there, it's also 3 volts on the other side. And that's extremely important because remember what we said earlier, that when we originally drew the problem, we also had this variation, minus 15 volts. We had here the 20 ohms. And we figured out that this was 5 ohms, but because the 20 and the 5 are all on the same series track, right? They're all on the same series track. That means that the 0.6 amps is the same as the 20 and the 5 ohms resistor. So I multiply the 0.6 amps and multiply by the 5 ohm resistor, which is equivalent of the 10 and 10 in parallel. I also have gotten the 3 volts, which definitely shows me two things. Number one, that the voltages across the parallel pieces are the same, which is fundamentally important to us. And it also shows you that we could have also foreshadowed this answer a different way as well, which I'll show you guys if you haven't seen it on your own by looking at the example in a different light in a moment. Okay, so now if we look at the problem, we have here positive, negative, positive, negative, positive, negative again because of the convention of the positive side of our voltage source entering this 20 ohms. So then it has to go here's positive and here's positive because the flow is going like this. And then they all go back to ground. And now we can see that for our entire problem, that in order to get the voltage across this entire problem, well, we know that 0.6 amps, right, was going through the main I source times about a 20 ohm resistor. That means that was giving us 12 volts, right? That 12 volts is the voltage drop. And then the 3 volts across the 5 ohms is also a voltage drop of 3 volts. So check this out. Our entire problem here through KVL states that we have here minus 15 volts, right? If I start at A and I go clockwise through, I read this polarity of each thing that I see individually. I hit the minus 15 first, the positive 12 next, then the positive 3 next. Gives me minus 15 plus 12 plus 3 equals 0. And that satisfies our Kirchoff's voltage law. So that's how we get started. This is how we do it, and hopefully you learned something, and I look forward to doing a few more of these videos as well, and I'll do some example problems, go a little bit slower, and answer more problems like this as well. But there's so much you can do with just the basics of getting down KCL, KVL, Ohm's law, and getting an idea of voltage division, current division with practice. You know, I generally like the rule of thumb. You need to do a minimum of 3 of these problems to get the hang of it. 5 to start to get to understand it, 10 to maximize and understand it well. So hopefully this is one problem to get you started, and I'll do 3 more for the next video, and then we'll go on from there. All right, it's been great.